So now that we have brushed up our basics on electric fields, let us see if we can apply that knowledge to understand how to compute the electric field distribution within a dielectric material, because that's what we will be using for electrical insulation. And we need to know how the electric stress is distributed within a dielectric material. Now, dielectrics are materials which are capable of storing energy, electrostatic energy. And where does the energy come from? The source of the energy is, of course, the external field. And the storage of this energy within a dielectric takes place due to a shift in the position of bound internal charges. What do I mean by the shift in position of bound internal charges? The actual mechanism of, I'm of course talking about polarization, but let us see how that relates to bound internal charges. The actual mechanism by which charge displacement takes place inside a material depends on the material. So you apply an external field, and within the material there will be charges which will be displaced in some manner, and because of that displacement of the charges, you will be able to store energy. Let us see how that happens. But the point that I'm trying to make here is, let us imagine that no matter what the physical process is, what happens is that when you apply an external electric field, the charges within a material get displaced and they form dipoles. And for the moment, what we will consider is any dielectric material, we will consider to be a free space arrangement of microscopic electric dipoles. So we will imagine that we have vacuum, and in that vacuum, we have a collection of dipoles. Where did that dipoles come from? How did that happen? I will discuss. But a dielectric material at the moment, we can look upon as a free space arrangement of microscopic electric dipoles. If I say that, what do I mean by dipoles? A dipole is a situation, a dipole is created when you have equal and opposite charges separated by a finite distance. So if you look at this picture, you've got plus q and you've got minus q, equal and opposite charges, and they're separated by a finite distance, small d. Now, a dipole as a whole will have a potential, will cause a potential to be experienced at any arbitrary point P. So let's take this point P. The potential V at this point P due to this dipole can be computed as the addition, the resultant of the force, the potential at P due to charge plus Q, and the potential at P due to minus Q. So if you do that, then the potential V at point P due to this dipole is given by QD cos theta by 4 pi epsilon naught r square. So as you can see, the potential is directly proportional to Q into D. The product Q into D is called the dipole moment, small p. Cos theta, the theta is the angle that is subtended by the dipole axis on point P. R is the distance of the center of the dipole to the point P, and epsilon naught is the permittivity of free space. So therefore, the potential is proportional to the dipole moment and inversely proportional to the distance from the point. E is, of course, can be calculated as minus QD cos theta by 4 pi epsilon naught r cube in the AR direction, minus QD sin theta 4 pi epsilon naught r cube in the A theta direction. So this is a dipole. Now, in a dielectric, where do these dipoles come from? Why am I looking at dielectrics as a conglomeration of dipoles? Now, there are two, of course, the process that we're going to talk about is polarization, but polarization happens differently from material to material. We will discuss that in greater detail at a later, in a later chapter. Right now, we will just talk about the dipole creation. Now, there are two kinds of materials. There are polar materials and non-polar materials. Polar materials are materials which already have permanent dipoles. Even when there is no external applied field, there is a permanent dipole. So maybe the molecules are such that because of the bond length, because of the bond angles, there is a unbalanced charge, there is a plus minus q with the distance of separation, there is an effective dipole. But ordinarily, when you do not have any external applied field, these dipoles will be randomly oriented and their effects will cancel each other out. So macroscopically speaking, the material will behave as a neutral material. However, those permanent dipoles are there, and when you apply an external electric field, these dipoles will align themselves in the direction of the field. If you have a non-polar material, you do not have any polar dipoles to start with. However, when you apply an external electric field, dipoles are created. How are dipoles created? Dipoles are created by a shift between the negative and positive charge center. Let me take the simplest example of an atom. In an atom, you have the positively charged nucleus, and around that you have the negatively charged electron clouds. Ordinarily, when there is no external applied field, the charge center of the positive nucleus coincides with the charge center of the negative electron cloud. As a result, the atom behaves in totality as a neutral particle. When you apply an external electric field, the electrons will move in the direction of the electric field, and the nucleus will not move, and therefore you will have an effective separation of their charge centers. So you will have an effective distance, a finite distance between the positive charge center and the negative charge center. So now you have equal and opposite charges separated by a finite distance, and therefore you have a dipole creation. Similar things can happen by charge separation between anions and cations and molecules and so on and so forth, but that we will discuss later. So what I am trying to say is that in a non-polar material, the first thing that needs to happen is when you apply the external field, firstly the dipoles have to be created. Once the dipoles are created, they will align themselves in the direction of the electric field. So P, as I said, is the dipole moment, which is equal to Q into T. The total polarization moment is the summation of all the dipoles per unit volume. So if you have n number of dipoles in a particular volume, in a unit volume, then P total in that volume will be summation Pi, I going to 1 to n. And from there we can define what is called polarization, capital P, which is summation Pi, that is the total dipole moment divided by the volume delta V, so dipole moment per unit volume in the limit delta V tending to 0. So polarization is again a vector quantity which is defined as the dipole moment per unit volume. So this is what happens when you have an electric field applied. So this is your positive electrode, this is your negative electrode, and you have got these dipoles inside. As soon as the dipoles might have been there, or the dipoles have been created under the application of the external field, no matter what, when these dipoles have been created, they line up along the direction of the field. The negative charge centers are pointing towards the positive electrode, and the positive charge centers are pointing towards the negative electrode. So they line up in this direction, and this process is called polarization. Remember, these charge centers are not free to move away from each other. They can move around their fixed positions, but they do not have an entity. They cannot have the positive charge cannot free itself from the negative charge. The negative charge cannot free itself from the positive charge. They are held together, and therefore they are called bound charges, and they are internal charges. They stay within the volume of the material, and they are called bound charges. Whereas when you apply an electric field on two electrodes, you are bringing charges from somewhere and placing those charges on the electrode plates. These charges that come from the supply and are positioned on the electrode plates are free to move under the application of any external electric fields, and they are called the free charges. So in this course, we will have to be very careful about distinguishing between free and bound charges. Free charges come from the supply and are supplied. Work needs to be done to bring them from infinity and put them somewhere on the electrodes, as long as the dielectric does not break down. However, polarization involves the movement of internal bound charges. There are no free charges involved.